Alright, what's going on? So I'm gonna record this video. It's gonna be a little different than some of my other videos. So like, you're given this problem, but I've already actually solved it. I solved it like in the middle of the night. So when it like first came up, I didn't really want to record a video then. So this is not me solving it live, but I'll go over this solution, but this solution is not like this solution is from the discussion, which I'll provide the link below for the discussion that for the person who posted this on the discussions. I didn't really improve on it much. I think I can do this to improve on it, do else, but I'll go over the main idea behind this solution and how it works. So don't know how to do this, but like the problem is just asking, you're given a complete binary tree. Here's a complete binary tree. So a complete binary tree will have, it will fill in each level, except for the last level may not be full of nodes. So like it's missing a node right here, but this is a complete, and you fill from left to right. So for instance, if you want to count the number of nodes here, you count 6. So for this problem, I'll say what my solution was. So my solution that I came up with was, the time complexity was O of n, and it was basically a breadth first search, a BFS search, by searching every level. It's very basic searching. I guess I can encode that, but the thing is that I'm not going to bother encoding it because the BFS it's not as efficient. So someone had a solution that was that works better than O of n. This solution is O log of n squared, which is way better. It's not as good as log n, but log n squared is better than O of n. So this is really good time complexity, so that's why I kind of went with this solution. So I'll go over the main idea behind it real quick. So basically what you do to count nodes is you're going to get this left depth. So you start at the root, which is usually you start at the 1 here, and then you get the depth for the left, and you get the depth for the right. Computing those depths is really just 1 plus and then recurse. Basically just go, but one thing here is that you're getting the left depth. That means you're always traveling to the left, if that makes sense. So like if you're here, let's see, I need something to draw with. Oh, this is such a bad video. I don't know if I really even have anything to say about this. That's even useful. So you have a 1, I think a 2, 3. I'll make something a little more bigger than this because I feel like, this is a bit, so I'll make a little larger example so that I can't do 8. So bad. This is so bad, sorry. Yeah, I'll just do this example. So we start this one, and we're like, okay, well, let's get the left depth and the right depth. So obviously, this depth and this depth, it's going to go down 1, it's going to do 1 plus 1, and it goes to the left, so it's going to go 1, 2, 3. So it's going to get 3 for the left depth, and it's going to get 2 for the right depth. Now, since they're not equal, what that means is, this is the thing that this person came up with. It's absolutely brilliant. I give him, like, whoever came up with this was, like, it's genius. I don't know, I'm still trying to get to that level. But, so here you return power 2. So you're doing 2 to the power of the right depth. And then you're calling it on the left. So, like, this is if it's not equal. So if they're equal, you're going to do this. But if it's not equal, you do this. And what does this really mean, this else statement? You're doing 2 to the power of the right depth. Well, okay, the power of the right depth is 2, right? So it's 2 to the 2. So you're saying 4 nodes, right? Is that correct? Yeah, because you have 1, 2, 3, 4 nodes. And not only that, when these are not equal, when the left, because 2 does not equal 3, that means that the right subtree is a complete binary tree. And if you look at it, this is a complete binary tree. I mean, it's not just complete, it's a full complete binary tree. I don't know if that's the right terminology. I hope that's okay. But I'll just explain what I mean, because maybe full is not the right word to use. But I just mean that because the level is not skewed at all. Like this this level is full, right? In the subtree, it's just the root. This level is full because it can have at most 2 nodes, and it doesn't have less than 2 nodes. That's what I mean by full. And for some reason, whenever you do the computation 2 to the squared, or you take the depth, that will give you the thing starting from here. Because I mean, this would be 3 plus 1, right? If this is a full subtree with depth 2, it's going to have 3 plus this 1. Okay, so we do that, and then once you do that, you're going to call self.count nodes on the left. So you go to this node now. So you're not at the 1 node anymore, you're at this node, and this node, you're going to look at the right depth, or left depth, and you're going to look at the right depth. So the right depth is just 1 this time, and the left depth is 2. So again, they're not equal. So because they're not equal, that means that this is a full complete subtree. I mean, it's just one number this time because it's just depth 1, so you just do 2 to the 1, which makes sense because you have 1 node and you have this one, so you add 2 more nodes to your thing. Okay, and then you go to this node because you go root dot left. So at the 4, you're going to look at the left and right, and this time they both have depth 1, so they're equal, and because they're equal, that means the left subtree is complete, so you do 2 to the 1, which will give us 2. So we'll call this entire thing, and then we're going to go to the root dot right. So far we've counted 4 plus 2 plus 2, so we're at 8 nodes so far. And we're going to call, it calls the root dot right here. So then when you call root dot right, it's this 9. It's 0 length for both the left and the right subtree. That's why you have these base cases. And because of that, this is really bad. I feel like I'm just like talking and like I don't know if I'm making any sense. So there's like you do 2 to the 0 power, which is 1. So if you have 0 depth for both, it's just going to count a 1, which is true. So we end up getting 9 nodes, which is the correct count. And while this is nice and all, I did want to show another example. I guess the one that they had, because there's something rather interesting about it. Okay, so here we have this, right? So I want to show this one because the interesting thing is that when you start at node 1 and you look to the left and you look to the right, both of them are length 2, right? Because they're equal, you know that the left subtree is fully complete, right? And it is, so you do 2 to the 2, which is 4, which is correctly the number of nodes, and then you go to the right. Yeah, so that's basically how it works. And I've already submitted it and it works. I can submit again. I changed this to an else. I think that's the only thing I really changed from his code. His code is just so nice. And yeah, so that's why I'm going to include his link as a link to the discussion. Wait, what am I saying? I'm going to leave a link to the discussion post that's about this solution. Yeah, so it's just a cool little trick. I didn't really realize you could do this to be able to solve this problem.